So far, we've seen a number of supervised learning methods, and when applying each of these methods, we followed a consistent series of steps. First, partitioning the dataset into training and test sets using the train-test split function, then calling the fit method on the training set to estimate the model, and finally applying the model by using the predict method to estimate a target value for the new data instances, or by using the score method to evaluate the trained model's performance on the test set. Let's remember that the reason we divided the original data into training and test sets was to use the test set as a way to estimate how well the model trained on the training data would generalize to new, previously unseen data. The test set represented data that had not been seen during training, but had the same general attributes as the original data set, or in more technical language, was drawn from the same underlying distribution as the training set. Cross-validation is a method that goes beyond evaluating a single model using a single train test split of the data by using multiple train test splits, each of which is used to train and evaluate a separate model. So why is this better than our original method of a single train test split? Well, you may have noticed, for example, by choosing different values for the random state seed parameter in the train test split function when you're working on some examples or assignments, that the accuracy score you get from running a classifier can vary quite a bit just by chance, depending on the specific samples that happen to end up in the training set. Cross-validation basically gives more stable and reliable estimates of how the classifier is likely to perform on average by running multiple different training test splits and then averaging the results, instead of relying entirely on a single particular training set. Here's a graphical illustration of how cross-validation operates on the data. The most common type of cross-validation is k-fold cross-validation, most commonly with k set to 5 or 10. For example, to do 5-fold cross-validation, the original dataset is partitioned into 5 parts of equal or close to equal size. Each of these parts is called a fold. Then a series of 5 models is trained, one per fold. The first model, Model 1, is trained using folds 2 through 5 as the training set, and evaluated using fold 1 as the test set. The second model, Model 2, is trained using folds 1, 3, 4, and 5 as the training set, and evaluated using fold 2 as the test set, and so on. When this process is done, we have 5 accuracy values, one per fold. In scikit-learn, you can use the cross-val score function from the model selection module to do cross-validation. The parameters are, first, the model you want to evaluate, and then the dataset, and then the corresponding ground truth target labels or values. By default, cross-val score does 3-fold cross-validation, so it returns 3 accuracy scores, one for each of the 3 folds. If you want to change the number of folds, you can set the CV parameter. For example, CV equals 10 will perform 10-fold cross-validation. It's typical to then compute the mean of all the accuracy scores across the folds and report the mean cross-validation score as a measure of how accurate we can expect the model to be on average. One benefit of computing the accuracy of a model on multiple splits instead of a single split is that it gives us potentially useful information about how sensitive the model is to the nature of the specific training set. We can look at the distribution of these multiple scores across all the cross-validation folds to see how likely it is that by chance the model will perform very badly or very well on any new data set. So we can do a sort of worst case or best case performance estimate from these multiple scores. This extra information does come with extra cost. It does take more time and computation to do cross-validation. So for example, if we perform k-fold cross-validation and we don't compute the fold results in parallel, it'll take about k times as long to get the accuracy scores as it would with just one train test split. However, the gain in our knowledge of how the model is likely to perform on future data is usually well worth this cost. In the default cross-validation setup, to use, for example, 5 folds, the first 20% of the records are used as the first fold, the next 20% for the second fold, and so on. One problem with this is that the data might have been created in such a way that the records are sorted or at least show some bias in the ordering by class label, For example, if you look at our fruit data set, it happens that all the labels for classes 1 and 2, the apples and the mandarin oranges, come before classes 3 and 4 in the data file. So if we simply took the first 20% of records for fold 1, which would be used as the test set to evaluate Model 1, it would evaluate the classifier only on class 1 and 2 examples and not at all on the other classes 3 and 4, which would greatly reduce the informativeness of the evaluation. So when you ask scikit-learn to do cross-validation for a classification task, it actually does instead what's called stratified k-fold cross-validation. The stratified cross-validation means that when splitting the data, the proportions of classes in each fold are made as close as possible to the actual proportion of the classes in the overall data set, as shown here. For regression, scikit-learn uses regular k-fold cross-validation, since the concept of preserving class proportions isn't something that's really relevant for everyday regression problems. At one extreme, we can do something called leave one out cross-validation, which is just k-fold cross-validation with k set to the number of data samples in the dataset. In other words, each fold consists of a single sample as the test set and the rest of the data as the training set. Of course, this uses even more computation, but for small data sets in particular, it can provide improved estimates because it gives the maximum possible amount of training data to a model, and that may help the performance of the model when the training sets are small. Sometimes we want to evaluate the effect that an important parameter of a model has on the cross-validation scores. The useful function validation curve makes it easy to run this type of experiment. Like cross-val score, validation curve will do threefold cross-validation by default, but you can adjust this with the CV parameter as well. Unlike cross-val score, you can also specify a classifier, parameter name, and set of parameter values you want to sweep across. So you first pass in the estimator object, or that is the classifier or regression object to use, followed by the dataset samples x and target values y, the name of the parameter to sweep, and the array of parameter values that parameter should take on in doing the sweep. Validation curve will return two two-dimensional arrays corresponding to evaluation on the training set and a test set. Each array has one row per parameter value in the sweep, and the number of columns is the number of cross-validation folds that are used. For example, the code shown here will fit 3 models using a radial basis function support vector machine on different subsets of the data, corresponding to the 3 different specified values of the kernel's gamma parameter. And it returns 2 4x3 arrays, that is 4 levels of gamma and times 3 fits per level, containing scores for the training and test sets. You can plot these results from validation curve as shown here to get an idea of how sensitive the performance of the model is to changes in the given parameter. The x-axis corresponds to values of the parameter, and the y-axis gives the evaluation score, for example, the accuracy of the classifier. Finally, as a reminder, cross-validation is used to evaluate a model and not learn or tune a new model. To do model tuning, we'll look at how to tune a model's parameters using something called grid search in a later lecture.